Morning. Let's start. So welcome back. I just had a couple of announcements. So everyone probably knows that the homework is due today by the end of the day, and the next one will be released right after the class. There's no class next week because I will be away, but the programming assignment is due on Friday, and I can't hold office hours because I won't be here, but all the TA office hours are still on next week at the usual time. So you have until Friday, and you can submit it until Sunday, but we will put out PA3 on Friday, and we'll have a similar situation as last time for the team signups again for PA3. So it'll just be exactly the same. There's an announcement yesterday, I think, because somebody from PACE contacted me, and he said some people, I wasn't sure whether it was the in-person class here or there's an online HPC class as well, but they had some high computational load on the cluster, so they asked me to check what was going on. So if people are requesting a high amount of computational resources, like more than 100 gigs or 200 gigs, please request fewer resources because you shouldn't need that many gigs. In the announcement, there's an example of the commands you can use to request fewer resources, just the amount that you need. And the last one, we will swap classrooms when I come back. That Monday is 3:10, because the class that's in this room, East Architecture 123, is having an exam, and their room is bad for exams. So we're just gonna swap one day. Other questions, concerns, issues? People are doing the programming assignment. I think so. Yeah, because people are using the cluster. So yeah, I think there's one more thing, but I kind of forgot. Oh, we will try to release the exam grades either today or in the next couple of days. We still have a couple of makeup exams to give, so we can't release the test paper, but we can release the numerical score. And once the makeup exams finish, we can release the test paper, and then people can ask questions or make regrade requests or anything like that. So yeah, any concerns, issues? Somewhere between 60 and 70. Other questions? It depends on the section too, like the undergrad section and the grad section. They're different. So when we release the exams, I will also make an announcement with the statistics like mean, median, standard deviation, stuff like that. Other questions? Okay, great. So let's continue. We're going to go on with dense matrix algorithms. So last time we were doing sparse matrix vector multiplication, and we had done 1D partitioning, which is you have a matrix and you have a vector, and you cut up the matrix just row by row. So if you have your matrix is n by n, and if you have n processors, then you can put one row on each processor, and then you put the entire vector on each processor, and you can do the dot product. This is the row and the vector, and each processor would calculate one entry of the output vector y. Because each entry in the output vector is the result of one dot product between one row and the entire vector. Another partitioning is 2D partitioning, which is rather than cutting up along just the rows, you can cut up along just the rows and the columns. And that allows you to use more processors, but it adds some additional complication because now you cut up along the columns, so each processor is calculating some partial result of the dot product. Rather than before with 1D partitioning, each processor was responsible for at least one output entry. Now each processor is responsible for partial results of each output entry. So we have this n squared matrix, and suppose in this extreme case that p equals to n squared. So we have one processor per matrix element. And the n by n matrix is partitioned across to this n squared processors, and each processor has one element in the matrix, and the n by 1 vector x is distributed along the last column of the processor grid. So we have an n by n grid of processors. We have n elements in the vector. So in the beginning initial distribution, there's only n elements in the vector. They have to be on some n of the processors. And one way logically to think about it is that they're just on the last column of processors, because like when you imagine the sparse matrix vector, it's like a matrix and a vector vertically like that. So that's why the reason for this initial distribution, and we can give algorithms given this initial distribution. So this is the steps of the algorithm. This is the initial distribution that we have. Each element is on one processor, and then we have this vector x, which is along the last processor column. And so to do the dot product, every processor needs some element of the input vector, and those elements need to be copied across processor columns. So like when you think about the different dot products, the first element in each row requires the first element in the input vector to do the dot product. And the second element in each row requires the second element in the vector, so that's one processor column for each one. So the first step is we have the vector x here, we align it along this diagonal. So if we had arbitrary sending, we could just directly send it. If we actually had a true grid, this would take root p steps to send it because you have p processors and the side lengths of the grid are root p by root p. And once we finally align this, then we can broadcast along the processor columns like this. And there's a question last time about why do you need to do this initial alignment step? Why don't you just directly broadcast along the columns? You can, but then this column also needs to receive a broadcast, and it cannot receive the broadcast while it is doing the broadcast. So doing this initial alignment allows the broadcast to happen truly in parallel. So yeah, it's a really good question. It was a bit subtle, but yeah, so the issue is that if you just directly, like you could just directly broadcast this along here, because we have algorithms to do broadcast from arbitrary root, like we did when we were doing communication primitives. But like if this one is broadcasting here, it cannot be receiving the broadcast, and it would need to be receiving the broadcast from this one, because this element is broadcast here, this element is broadcast in this column, and so on, and then this element is going to be broadcast in that column. So yeah, so there's this alignment step, then there's the broadcast along each column. After doing, so everybody does a multiply as part of the dot product, and now we need to reduce horizontally because every processor row has one entry of the dot product, but we need to add them all up. So now we just do reduction along each processor row. And this is going, once we reduce along the processor row, the final element of the output vector is going to be along this last processor column. Questions? Okay, so we can analyze this algorithm. The first step is to align this along the main diagonal. This is assuming if we have a hypercube, we can do this in log n time because the maximum path is n, and with a hypercube, the maximum path between any two nodes in the hypercube is log n because there are log n bits in the thing, and each one gets flipped once to go to the neighbor. So that's why this extra factor of log n, this tau plus mu, because we send only one element from the vector to align it along the diagonal. Then the next step is to do this broadcast. So there are n processors in the column, and we have the algorithm for broadcast, and we had the primitive runtimes for broadcast, which depends on the number of processors, which is log in the number of processors multiplied by tau plus mu, the message size. And here the message size is also 1 because we're broadcasting one element, so that's why it ends up like that. Everybody, now once you have the vector element, just does local multiplication. That just takes unit cost in our model. And the final step is to do this reduction along the row, which has this communication cost, tau plus mu log n, plus log n computation cost. And these all just come from the communication primitives that we learned in the previous lecture, but this is how you use them to make an algorithm like you. Yeah, you just combine them to aggregate your data or do reduction or broadcast or anything like that. Okay. So the communication time is just you add up the communication steps, which is everything involving tau or mu, and we get tau log n plus mu log n. which is these two combined. These three terms are just order this thing, because it's a constant number of steps. The computation time is log from the reduction. Is this algorithm efficient? Why? Mhm. Yes, good, exactly. So it is not efficient because we have n squared processors, and we need serial time over p. So like if you remember, the work is the processor time product, the time over all the processors multiply the number of processors we have. So we have n squared processors, and the parallel time is log n. So that means the processor time product is n squared log n, and the serial time was n squared. So exactly, it is not efficient. Yeah, so we need order 1 runtime because we have n squared processors, and the work is n squared. Questions on that part? Okay. So it was not efficient, so we cannot use up to n squared processors to achieve maximum efficiency. So we're going to use fewer than n squared processors. When we have fewer than n squared processors, the difference is that rather than each processor having one element, each processor has a submatrix of elements. And actually, the submatrix that it has is size n squared over p, which each dimension is n by root p by n by root p, because you have a p processor grid, and so each side is root p. And this accounts for all the matrices, or the entire matrix, because you have n squared elements in the matrix, and there are p processors. So you just divide it up as evenly as possible over the p processors. And finally, the vector is distributed now in pieces of size n over root p in the last processor column. So this is similar distribution to when we had n squared processors, but just with submatrices and subvectors rather than one element of the matrix and one element of the vector. Yeah. And so in that case, we can perform the same steps as before. Like the steps are alignment, then broadcast, and then multiplication and reduction along the columns. But now, rather than size 1, this is size n over root p in the message size. And the things that are being communicated are size n over root p, because like the submatrix size is n over root p, but every processor is computing some partial result of y, and that is going to become n over root p. This is just like an example with 4 processors. Okay. Yeah, the computation is this size, this size matrix times this size vector. So n squared over p matrix times n squared over root p vector. And when you come to the serial case, you just run the serial algorithm for matrix vector product, like row, column, dot products. Okay. So we can do the analysis in this case. So for p is less than n squared, we're just doing the same algorithm, but now the message size is bigger. So first step was to align the vector along this main diagonal, and that's communication time. So how much would it cost us to align the vector along the main diagonal? Mm-hmm. Yep. Yes. Yeah. So if this is assuming that we have we can directly arbitrarily send. But if we have like a hypercube, then it's the same logic. We have tau over, or we multiply the whole thing by log of square root p. And so this comes from, so tau is the startup cost, mu is the bandwidth factor, and n over p is the size of the vector that we're sending. And the reason that this is log of square root p is because one dimension of the vector is square root p. Or sorry, one dimension of the processor grid is square root p, because the whole thing is p. So like the grid is root p by root p. So you just have to send along one dimension. Okay. Second step is to broadcast the vector elements along the columns. So all the broadcasts can happen in parallel. So the cost of this in the asymptotics is the cost to do one broadcast. And how much is it? Well, you can get it by reasoning about how many processors are in each column and what is the message size per processor. And then you plug it into the broadcast time. Sorry, this is a question. What do you get when you plug those things in? We can start from the sub-questions. So how many processors are in each column? Repeat. So there are root p processors in each column, and the message size per processor that we have to broadcast is n over root p, exactly. So you'd plug those in. Each column has root p processors, and the message size is n over root p. Because, yeah, and so this is just the broadcast time, like the broadcast time that we had in the primitives, but we plug in root p for the number of processors and n over root p for the message size. Sure, yes. So this thing, like you have to send, so the vector is in the last column, and you want to send it to like along the main diagonal. And if you actually truly had something like a hypercube, you would have to pay an extra log root p factor, because the path through the graph is at most log root p. But this is like a very optimistic assumption, which is like assuming that you can just directly send point to point with no extra factor. That's what this is. But if you had a hypercube, you would have to pay this extra log root p factor. And if you had a true grid, you would have to actually pay like root p, because if it's a grid, like just look at the top row, you have to send from the right all the way to the upper left corner. So you have to do like 1, 1, 1, 2, which is length root p. It doesn't, is the question like, oh, yes. So it doesn't assume this doesn't affect the broadcast. Well, this is necessary to do all the broadcasts in parallel, because you have to do the initial alignment. But it doesn't affect the broadcast runtime, because this alignment happens before the broadcast. Yes? Is the assumption that we have a direct connection different from when we had p equals n squared? Let me go back. No, here we assume we have a hypercubic connection, because this extra factor of log n is here. And if we had a direct connection to align this vector along the main diagonal, in this case, it would just be tau plus mu. We just send directly to the diagonal. I think it was just in the slides for simplicity, but to get under the same assumption, you would multiply that other thing by log root p. Yeah, but when you have to figure this out, like if it's on the exam or something, I'll say, oh, like what kind of connections to assume. So we have done this broadcast. The column size is root p processors. The message size is n over root p. Yeah, because this is 1/2 log. Yeah. Yeah, in the big O, yes, exactly. The root p would go away. It could just become log p. Yeah. Okay. So when you broadcast this, that's it. And now we do the computation part, which is this local multiplication. And so how long does it take us to compute this local multiplication? Well, how much of the matrix is on each processor? Good, yes. So the local multiplication takes n squared over p because we have n squared over p elements of the matrix on each processor. And finally, the last partial reduction part is basically the same as the broadcast. So the message size is per processor, and then now we do the primitive along the row rather than along the column. But the same idea, and we get the same runtime. This broadcast time matches this reduction time because each row also has root p processors. The message size continues to be n over root p, and this is what happens when you plug it into the reduction time. So reduction and broadcast have the same asymptotic times when you look at the primitive runtimes. And yeah, you can simplify this root p. In the big O, it could just become log p. Yeah. So this is pretty much how these analyses go. Like you have these steps, and the steps are either local multiplication or based on some communication primitive, and you have to figure out what is the size of either the subcomputation in the multiplication part or the size of the message that you're sending, and the size of the message, how many processors are involved in that, and which communication primitive is it. Yeah. So finally, when you add them all up, the communication time is determined by the time of the broadcast and the sum, but there are two of them, so they just add up to big O of that thing. The computation time is n squared over p. And this is a good thing to check, that indeed it is n squared over p, because ideally we would like to achieve serial time divided by p, and that is what this is, so that's good. And it's efficient up to n squared over log squared n processors. Yeah, and so this can use up to more processors than the 1D implementation, because 1D can only use up to n processors. Like if you can only you have to put at least one row on each processor in the 1D case. It doesn't make sense to use more than n processors because you only have n rows. Question? Okay, so there are no questions. We can move on to matrix-matrix multiplication, which is another dense matrix algorithm. Yeah, so we are familiar already with matrix-matrix multiplication. We have done it when we were doing caching. We did it when we did workspan. And the reason that we keep revisiting it is like it's one of these classic problems in high-performance computing. Like people have spent past like 50 years trying to optimize matrix-matrix multiplication, and you think it's over, and every year there's another paper about it. So it's still a relevant problem, and it's kind of like this important case study for us because they're nice baselines. Like people have spent a long time optimizing it, so we have good libraries for it, and so like you have a sense of like how far you can go with your optimization. Anyway, so to recap, for matrix-matrix multiplication, we have two matrices, we have three matrices, A, B, and C. A and B are the inputs, C is the output. And for now, let's just assume that they're all square. So they're all n by n. If they're all n by n, the serial complexity of this is n cubed. And we have this simple 3-loop implementation over ij and k, this for each I and j in C, you compute some dot product. So k is the fast-moving dimension, and you set Cij to the result of the dot product between one row of A and one column of B. And the work is n cubed because there are n squared entries of C, and each one takes n to compute because you have to do a dot product of length n. So let's have this initial algorithm for matrix-matrix multiplication, and now we're going to do it for distributed memory. So suppose we have n squared processors, and it doesn't, so it makes sense to have n squared processors because the input size is order n squared. So unless you duplicate the inputs, then you're not going to have more than the data volume of order n squared. So it's easy to initially distribute the A and B, and also C, on the n squared processors because there are n squared elements, and so it's natural to assign each ij onto the ij in the processor grid. So to compute Cij, you need the entire row of A and this entire column of B. So suppose that you're trying to compute this 0, 0 entry, you need row 0 and column 0. However, in the initial distribution, we only had A00 and B00. So we have this problem, and this is kind of similar to the issue that we had with the 1D matrix vector. But we need the entire vector, but we only had one entry of the vector. So we can do a similar thing, which is that we all gather the data that we need to do the computation. So step 1 is that we can all gather the entire row of A onto this processor. Here in this case, we all gather row 0 onto processor 0, 0. And similarly, we can all gather the entire column onto this column, or onto every entry in this column. And for the row, we all gathered for every entry on the row. Because every processor in this processor row needs the entire data row. And every processor in this processor column needs the data column. And then once you have the correct row and column, you can do the dot product to get the correct Cij. And after this, everybody can compute individual Cij, and that's the end. Does the algorithm make sense? This is kind of similar to what we're doing in the matrix vector case, but just now the second operand is a matrix rather than a vector. So you have to do two algathers. Yeah, so the data requirement was like this. You have every processor is going to end up with one row of matrix A, one column of matrix B, and one entry of C. And then here, like in this example, for 2, 1, you need row 2 and column 1 of the data. So we're going to multiply these two n by n matrices to get an n by n matrix. The serial complexity is n cubed, and ideally we would like the parallel time to be something like n cubed over p. For now, we are not going to consider better serial algorithms. We have better serial algorithms for matrix multiply, like Strausson's algorithm, but in these standard libraries, they often focus on just the n cubed implementation. And you can also use, so at the high level, we use this n cubed implementation, but you could use these faster implementations in the base case on one processor. Yeah. So in reality, we probably don't have n squared processors because n squared can grow quite large. And so we have done matrix blocking already, but we're going to recap it. So if you have an n by n matrix, you can think of it as a q by q array of blocks, where q by q, in reality, like when we map it onto the processors, is going to be like q by q is equal to p, or something similar to p. And the goal is that rather than putting one element on each processor, you put a block of elements on each processor. So each block is going to be size n by q times n by q. And then we are going to perform q cubed subproblems. Each one involves size n squared over q squared matrices. And again, like n squared, q squared is like p. So if we do the blocking, this is basically the same thing, but so rather than holding an entire row and column of the data, we are now going to hold a block row and a block column of the data. So if we have process Pij, it stores initially Aij and Bij, and Aij and Bij are submatrices cut up along by this thing. They have size, each one has size n squared over p, because you have n squared elements and you have p processors, and then you can just index the blocks based on like the max length of I and j is root p, because the length of the processor grid is root p. And then if you want to compute the submatrix Cij, it's the same thing. You need the same data, except now it's just a block row and a block column. And we can do the same algorithm. You just all gather now blocks of A and blocks of B, rather than one row of A and one row of B. And so the actual, like the high level looks pretty much the same, which is that you get one whole row and one whole column, but now this row is actually several rows. It's n over root p rows. And this column is not just one column, but it's actually n over root p columns. And that's what you need to compute an n squared by p submatrix of C. Yeah. So yeah, we're going to do the same analysis. We have to do two altogether operations. What is this time to do these two altogether's? The argument follows a similar line. What is the message size that we have to send? And how many procs are going to participate in the altogether? Maybe we could start with the message size. So we're all gathering the blocks. Go back here. And each block has size n over square root p by n over square root p. So that is n squared over p. And how many processors are participating in this altogether? So is what we are all gathering clear? Like everybody has a block of A and a block of B. And we are all gathering the blocks of A along the row and the blocks of B along the columns. So how many processors are participating in each row altogether? Square root p, exactly. Because this grid length is square root p here. Yep. So there are square root p processors participating in altogether, and the message size is n squared over p. And this is, we just got this by plugging this into the runtime for all gather. Okay. And now we have to do the computation time. So we are going to multiply, in each processor, we're going to apply root p multiplications of this size, n squared over p. So how long does it take to multiply one do one submatrix multiplication of this size, where each submatrix is size n squared over p? N squared over p. The input size is n squared over p. If you have an input of n squared, how long does it take you to do the matrix multiply? Yeah, so let's just do for this, like maybe a simpler case, which is like if your input is an n by n matrix, like you have three matrices, A, B, and C, they're all n by n. What is the matrix multiplication time in that case? So if you shrink it down to n squared, your input size becomes n squared over p, then the multiplication time is, yes, exactly. So the multiplication time is n cubed over p, or n cubed over root p, I guess, because the length, it's cubed in the length of the matrix. The total time to do all the submatrices is n cubed over p. So maybe I can repeat that because it was a bit unclear. So if you have a matrix length of n, matrix multiplication takes time n cubed. If you have matrix length of anything like L, the time to do that matrix multiplication is L cubed. And so here L is equal to n over root p, that's the side length, and you cube that to get the time to do one matrix multiplication. You have to do root p of them, so that's where we get n cubed over p. And so, yeah, so this is good because we want, oh, yes, go ahead. Sorry, could you say it a bit louder? Yeah. This one, sorry. Yeah, so this is n cubed over p to the 3 over 2. And so like this is p to the 3 over 2 in the denominator. This is p to the 1/2 in the numerator. And so the bottom becomes p. Why aren't we doing p of them? Oh, yeah. So good question. So the length of the whole processor grid has p processors, but each row and each column only has root p processors. So when you all gather, like how many submatrices are you all gathering from your row? It has to be root p of them because there's only root p processors in your row, and same with the column. So that's why there's only root p subproblems. Does that make sense? Yes. Yeah. Yes, exactly. So each, before what was a dot product of single elements, now is a dot product of blocks. Yes, if we had one processor, then, so in this serial case, if we have one processor, then we can only do the n squared multiplication on the one processor. Yes. So are you asking like why is this root p? Yeah. So it doesn't make sense why this is this. Yes, good question. So the reason that this is multiplied by root p is, so we first all gathered root p, like how many submatrices did we all gather onto a processor? Just think about like processor 00 in the upper left column. We have to get all the blocks from the processor row and all the blocks from the processor column for A and B respectively. So how many blocks are we getting onto P00? From A, it is root P blocks because there are root P processors in our processor row. Yeah. And same with the columns. Good. Other questions on this part? So if we add up the total time is the computation time plus the communication time. And this is just what you get when you add them up. And this is efficient for P is on the order of n squared. So this is pretty good because it is unlikely that we'll have anywhere close to n squared processors. Are there any issues with this algorithm? Is it possible to replace the altogether with a broadcast? I see. Because you want to all gather like A and B at the same time, basically. Mhm. But don't you need a column of matrix B? Like you have a row of matrix A, and you need the corresponding column of matrix B to compute Cij. So how can you all gather the row of matrix B? Oh. Mhm. I see. Yeah, you can probably get this altogether down to one altogether, potentially. I have to actually think a little bit more about how exactly it works, but potentially. But it doesn't affect the asymptotic runtime. Um, so so what I mean with this is not exactly like in the runtime. Like the computation time is fine. We cannot really hope to do better than n cubed over p. Yes. Yes, exactly. Yeah. So we have to copy the submatrices, we have to copy the blocks, like the block rows and the block columns. And we had n squared originally in the input, and now we have to use an extra root p factor in memory consumption, because for every processor, we have n squared over root p elements. Yeah, n squared over root p elements. And we have p processors. So that's why the total consumption is n squared root p. And ideally, we would like the memory to be something like n squared over p, because we have n squared input and we have p processors. So yeah, so in terms of runtime, this is fine, but the major issue with this is that the memory is not optimal. So let's try to get this restriction, which is that we don't copy A or B across the processors. We only have one instance of each element in both input matrices, and also the output element. And suppose that so this is the same layout that we just had, which is that for ease of illustration, it's just one element on each processor, but these could also correspond to processor blocks. And for P00, we have A00, B00, C00, and so on. Like for Pij, you have Aij, Bij, Cij. This is our Nisserl distribution. And if we look at, let's just look at C00 for a second. So C00, this is the number, this is the multiplications and additions we need to compute it. So the outer dimensions are always 0 and 0, and the inner one changes, like 1. The inner one ranges from 0 up to n. And it's always the same for any Cij. The outer dimension is always matching Cij, and the inner one changes 0 up to n. That's just in the dot product. So to compute C00, we need, this is good, like we have A0 and B0, we have A00 and B00, and that is what we need to compute the first term. However, like now we need to compute the second term, and we don't have A01 or B10. But our neighbor has A01, and so our right neighbor has A01, and our down neighbor has B10. So we could do communication to push this B10 up 1, and communication to push this A01 left 1. And for the case of C00, we can keep repeating this process. Like, so we need A02 and B20. But here is A02, and here is B20. So if we kept doing, if we rotated the elements, then next A20 would be here, B02 would be here, and then in the next step you just do the same thing. Like the row rotates 1 to the left, and the column rotates 1 up. And then you would have what you need to compute this term. And then the same, you would do the same thing for 03 and 30. So that is good in a way, because now we only need exactly one copy of every element over all the processors. But we traded some. But the trade-off is that we traded some communication time for it. Like now we have to do communication in rounds. And this isn't going to immediately work for C01. So it works for C00, but it doesn't immediately work for C01. Like if we look at what we have here, we have A01 and we have B01. However, like A01 needs to multiply B11. So something like this is going to work, but we're going to have to do some initial alignment. Any questions on like this high-level plan? So the high-level idea is we're going to put only one instance of each element across all the processors, and we're going to trade some communication to avoid copying, and we're going to proceed in rounds. So we're going to proceed in, suppose that the length, so if the length of this is root p, we're going to do root p rounds. Mm-hmm. Yes, it would increase the communication time. So we're paying some communication time for reducing the memory usage. No questions? Yeah, so we want to have this high level thing where all the processors compute some component of their matrix multiplication in each round. And to do that, every processor needs to have two terms of A and B that match in this dot product, which means that the inner dimension needs to match and the outer dimension needs to be correct for the C that it has. Yeah, and like I was saying, this is not immediately right because it's not the right pair of A and B on this C01, but with some modification, we can get it to be the right one. And another high-level reasoning that we need is that you can compute these terms in any order because addition is commutative. So while C00 computes this first term, like A00 and B00, C01 can compute this one, A01 and B11. Yeah, so for this case, to do this initial alignment, we're going to send B11 up here to get the inner dimensions to match. So A01 needs to match B11 because both the inner dimension for A and B needs to be 1 to line up. Yeah. Questions? Mm-hmm. Question. We're replacing B01 with B11 because we want ideally only one copy of each element across all of the processors. And we can do that through like we had. You can just do that through like MPI send. I guess. Oh yeah, and this is another example. So we have for C01, we want to compute A01 and B11. For C02, we want to compute this term. We already have, sorry, it's blocked, but we already have A02, which is something that we need to compute C02. But the B is not right. The B needs to be 2, 2 to match up the inner dimension. And that's what this is. So the alignment cannot be the alignment method is not exactly the same for all the columns because here we needed to align this 1 up, and here we need to align this 2 up because B22 is here. And so so this is like one of the classic algorithms for distributed memory matrix multiplication. It's called Kenin's algorithm. And Kenin's algorithm basically goes in this high level, which is that each processor is rotating along its processor row and its processor column. And so we had the case for P00. P00 is the only one that immediately works. But so in the first step, P00 would multiply these red blocks together. And we're trying to output this. And in the next step, you left shift the A matrix. So this one left shifts this way, this one up shifts that way. So now this blue block lines up in P00. And you multiply them. And then the same, like you keep left shifting along the row and you keep up shifting along the column. Now the green blocks line up. And finally you do one more rotation and the yellow ones line up. And that's it. So like this is what is happening for P00. This is also happening for all processors. So each processor is participating in a left rotation and an up rotation. And the initial alignment makes it so that the initial blocks line up. And so when you keep doing the rotation, the blocks will continue to line up. Okay. So now we have this issue with P01. Like this is the same initialization that we had, but this is wrong because, oh yeah, so now you need red and red to line up here. Or sorry, 0, 1. Oh yeah, okay, sorry, yes. So you need blue and blue. So 0, 1 is here. And so these are the A and B that we're considering. So it's the same processor. But on 0, 1, we have this blue block of A, and on 0, 1, we have this red block of A. And so to do the initialization, we just rotate up 1 in the initial alignment, and now they are aligned, blue and blue. And if you continue doing this left and up rotation, then they will continue to be aligned. Yeah. So for processor, in another example, processor 2, 1, 2, 1 here. Neither of them are aligned, so this is blue and this is green. And so we can align them by shifting A left by 2 and B up by 1. Yeah. So the alignment step initially yeah, so first you shift A row-wise to do the alignment. And then you shift B up to do the alignment. And now this is 2, 1, here, here, and here, and both of them have the same color. Oh yeah, and then now the multiplication is just the same. You always rotate A 1 to the left, and you always rotate B up 1. So it's this. Red and red are matched, then blue and blue, and finally green and green. And the reason that they're matched is the colors are in the same order in both the row and the column. So if you align them right in the initialization, then once you keep rotating, they will continue to be aligned. So to do this initial alignment, suppose we have this processor PIJ. To align the blocks, you shift AIJ left by I steps, and you shift BIJ up by J steps. And so the reason for this is that you're trying to match the inner dimension. And by shifting AIJ left by I, you add I into the column index. You're moving. You move what was initially AIJ, you are getting A comma J plus I instead. And then similarly, when you shift BIJ up by J, you get BIJ and J. Like you start with AIJ and BIJ. Then when you shift A left, then you're adding to the column index. It's like, just think about the thing 1 to the right of you. Like if you are AIJ, the thing 1 to the right of you is AIJ plus I, or AIJ plus 1. And then so if you just continue to do that I times, then you will get AIJ plus I. And then similar for the row, similar for shifting along the columns. If you shift up 1 row, you are BIJ. You get what is from your bottom neighbor, that is BI plus 1, comma J. And then if you keep repeating that, J times, then you get BI plus J, comma J. So you keep the column fixed for J, or sorry, you keep the column fixed for B, and you keep the row fixed for A. But you are trying to match the inner dimensions. And then finally, after this initial rotation, PIJ is going to have AI J plus I mod root B, because we're just coming around in a ring in each row and column. And B is I plus J mod root B, comma J. And the important part is that both the inner dimensions are now the same. And the reason that we want the inner dimensions to be the same is because that is what you need to do the matrix multiplication correctly. The inner dimensions always have to be the same, and the outer dimensions have to match IJ when you're calculating CIJ. Any questions? Okay. So if we try to analyze this thing, there's like two phases kind of. One is the initial alignment, and second one is like you do the rotations and you do the multiplications. So in the alignment steps, the maximum distance by which a block needs to shift is root p minus 1. Because like in the worst case, every processor row or processor column has root p processors in it. So the most you can shift is along the entire row, which is root p minus 1. And two shift operations require, so you have to do two shifts. One is along the row and one is along the column. And that is going to take, this message size is n squared over p. The number of times you have to shift is potentially up to order root p. And so that's just what this is. Like this is tau plus mu n squared over p, the whole thing times root p. And the second phase is this actual computation and passing around of the data. That has also root p steps. So you see that it's root p steps because like the processor row and the processor column are both length root p. So after you have done root p plus 1 steps, you're just going to get back the initial data that you had. It's like you have some data, some part of I or some part of A, and you keep shifting it left in each step. And after root p step, it's going to come back to you. And this submatrix computation is the same. We still have root p multiplications. The submatrices are the same size that we had previously, which is n squared over p. And so the computation time is the same. We are doing root p submatrix multiplications. Each one costs n over root p quantity cubed. So the total computation time is n cubed over p. So this is good. Like we maintain the computation time. And again, this is kind of the best that we can hope for. However, we did have to pay in the communication time. So we have to do root p shifts. And each one takes tau root p plus mu n squared over p root p. Or sorry, each one takes this, tau plus mu n squared over p, and you have to do root p of them. So that's where this comes from. So you can see like it is more straightforward to think about these algorithms on the processor grid than to think about them like on the hypercube, for example. That would be a bit challenging. So that's the reason that we did embeddings first, which is like you want to achieve hypercube runtimes, like with allgather, for example, like we did in the previous algorithm, but you don't want to actually reason about them on the hypercube because it's quite complicated. Yeah. So the total time, you add them up, it's the computation time, n cubed over p, communication time, tau root p plus mu n squared over p. Questions? So if you have problems like this, they kind of go in a similar way, which is if there's an alignment step, first to calculate how much the alignment step costs, then you may have some compute and shift steps. And so in each step, you have to compute what is the size of the subproblem and what is the size of the subproblem in the data, and then that can give you the volume of computation in the subproblem. So like here, the size of the subproblem, one side length was n over root p. So then we got the volume of computation, which is by cubing this thing. And then we just multiply that by how many steps we had, how many compute and shift steps we had. And so that's the computation part. And in the communication part, you can reason about it by knowing how much data you are sending. So here, the amount of data we're sending is the submatrix size, which is n squared over p. it might not always be a square submatrix. Like there can be many algorithms for distributed matrix multiplication. But if they follow this compute and shift type, then you can, then you just reason about it like in these subparts. Like what is the size of the subcomputation step? What is the size of each communication step in the shift? And then you just multiply them with how many steps you have. So we did trade some communication time for this, but this is memory optimal because you always have to store at least one copy of each of the input elements across the entire processor grid. And here you store exactly one copy. You store exactly one copy of each element in the entire processor grid. Yeah. We don't have to go over this. This is the MPI code to implement Kennedy's algorithm. I think it's not worth it to go over, but basically the way it works, so like the way it works is that you do, this just implements the shift, the rotation, and the multiplication. And this is the this is like the serial case. This is the base case. So you can just implement this 3 loops. You will not have to implement Kennedy's algorithm. I have like 1 more minute, and so we're just going to wrap up here. But really quickly, next time we're going to continue on dense matrix algorithms, and we're going to try to resolve this one limitation, which is that it requires a square processor grid, and it also requires the matrices to be square. But in reality, you may not have a square grid, and you may not have square matrices. So we would like to get rid of this limitation. And we will continue this next time. Thank you.